This is a bit sort of a childhood passion. My father was a filmmaker, so he was a cinematographer and then turned director. So I grew up in a place where visuals were always getting made.
This is Appu Shaji, a machine learning engineer at Dropbox.
I liked sitting behind my computer and coding stuff up. So I thought, okay, fine. How can we sort of connect the art of visual storytelling and computer sciences?
Before coming to Dropbox in 2025, Appu co-founded a startup called Mobius Labs. They wanted to make it faster and easier for computers to understand the world around us, something he's been studying and thinking about for the last 20 years. Of course, his approach has evolved a bit from when he was younger.
My vision back then was to create a robot like Data in Star Trek.
Oh, wow.
So if you think about all the robots in Isaac Asimov or Data in Star Trek, it's seeing the visual world, it's hearing the visual world and navigating around the world, essentially. So this was sort of the childhood fantasy.
Unfortunately, Appu isn't building robots for Dropbox yet. But what him and his team are doing is almost as amazing. So most AI tools today work primarily with text. Web pages, documents, emails, PDFs. But at Dropbox, Appu and his Mobius Labs co-founder Hicham Badri want to make it easier for you to work with photos, video, and audio too.
In creative workflows, especially when people wants to edit, people wants to tell a new story, a lot of time is spent searching and finding that right clip. For example, one of the sequences in Jurassic Park where dinosaurs are being viewed by the two main characters for the first time, and there's a sense of awe, etc.
Imagine having to find that scene yourself with no prior context. It would probably involve a fair amount of poking through folders and scrubbing through footage, and that's assuming all of your assets are nicely labeled and organized, which, come on, we know they're not. But now,
I can just type in, okay, seeing the dinosaur for the first time, character surprised, and comes that particular moment.
Which is pretty darn cool. And I'm not just talking about the dinosaurs here. I'm Matthew Braga, and this is Working Smarter, a podcast from Dropbox about how AI is changing the way we work and get stuff done. Today, we're talking about audio and video and photos and all the things that Dropbox is doing to make your content searchable and understandable and more useful with the latest and greatest in multimodal AI. Appu and Hicham are going to explain how we got here, how they got here, and what kinds of things are possible when you can, say, search within a video, or ask questions about an audio recording, or find that one perfect photo in a folder of files with names like IMG_001. That's coming up next on this episode of Working Smarter.
I'm always very interested in actually building technology and making it usable for end users, because I feel that's when technology becomes really important. At Mobius Labs, we have always been interested in visual search from day one. So our product was a set of computer vision algorithms which can analyze images and later audio and videos that can be used by media companies to search through large collections of images or video collections. So our clientele were a lot of stock photo companies, etc. And Dropbox also had very similar problems. A huge set of Dropbox users are this media and creative user base, where searching through large content of video and audio and images is a profound problem. And solving search for these users is very important.
So how do you do that?
When you think about search, you also have to think about different kind of file types. Typically, people have docs, they might have Jira tickets, they might have videos, they might have audio files, etc. So search has to work across all of these different file types. It's kind of hard to know what is inside, what is happening inside a video document. So we run certain models to look inside the video. So if you think about video, it has various aspects. It has the visuals that you see within the video. Like I'm seeing you, Matt, and that's kind of a very visual input. We are talking to each other. That's essentially an audio input. And then we are talking in some language. So that's contextual in nature. So combining everything, this process is called multimodal input, where you have different modalities sort of merging. And you have to combine all of that things together, and using some of the powerful sort of AI models that is coming up. That's what we use. And once this data has been extracted, this should be prepared for search. So typically we use techniques like sort of good embedding models. So think about embedding models as creating a small summary of what something happens in a doc, so that the search engine can quickly go and retrieve that essentially. And then there are other layers like personalization. So every user should have a different experience based on what is important to doing their work. So for example, if I search for Q2 2026 roadmap, maybe someone who's working in content production has a different roadmap file that is important. So really finding that personalized content is super important. What we are building is that users files are scattered across multiple formats, multiple platforms, but you have a thought, you want to find something. How can you just use a text prompt and write it, and the search has to do its job seamlessly so that the top hits is what you want. So optimizing for that use case is what my team does.
Let's say in the past, I had a video and it has lots of different scenes in it, but I know that there is a scene of maybe a sunset in Berlin at night. And so in the past, I would have had to maybe have known the exact name of that file. I might have searched via the file name. Maybe I would have had to know what folder it was located in. But what you're saying is the stuff that you and your team has been developing allows you to actually type in, show me the scene in, that video I shot last week of Berlin at night, and it'll be able to find that. Is that correct?
Exactly. Because fundamentally, what the previous search engines were looking at was the file name, where it was located, etc.
Got it.
But actually what people want is that particular content in your example, that Berlin scene essentially. And because our models can look directly into the videos and understand, hey, this is a Berlin scene, hey, this is Berlin at nighttime, or maybe some people are walking, this is that famous monument there. That work will be done by the models automatically. So you don't have to do heavy work essentially. And this is a real big pain point for a lot of our users who are editorial team, who are content team, has to spend enormous amount of effort sort of processing, putting it in right folder structure, coordinating across teams, etc. So a lot of this heavy work, this is a lot of grunt work that people have to do, is now being able to be done by these machine learning models. And that saves a lot of time, especially for our target customers who are really creative storytellers, and their job is not really organizing files. They have to do it because that's the only way previously possible. But now we are able to go and free up a lot of their time to actually do the work that matters, rather than this grunt work involving folder arrangement and sort of adding metadata tags, etc. Minimizing that time is the main sort of the motivation of the work that we do, so that people can tell better stories, faster stories, and clearly make cooler narratives moving forward much easier.
You used that example a second ago of Berlin at night, and I'm wondering if you can walk me through all the different things you're doing to understand what's happening in that scene. Like, is there a list of different objects or elements or just things that the models are looking for?
So there are maybe 2 or 3 aspects to it. One is, what does this bunch of pixel constitute to be a Berlin? Because these models have seen a lot of previous Berlin photographs or visuals previously, inside the network, it has an idea about what Berlin looks like. That means certain neurons in this transformer networks will fire for this pixels which resembles these facades of Berlin or idiosyncrasies of Berlin. Similarly, nighttime also has a certain pattern to it. Again, because we learn these network with large amount of data, there is again a certain activation patterns for these. And together, Berlin in nighttime, there is even a specialized activation patterns that happens in this particular network. And this is actually quite remarkable to think about this because we are not explicitly telling, hey, this is Berlin or this is nighttime. Because it has seen a lot of data, it's able to do that.
What about more advanced examples? Like you gave that Jurassic Park example where, there's scene changes, there's different people on screen, later on when there's dialogue introduced, there's different people speaking, audio cues, like there's all of these different factors that you also have to take into account. And I'm wondering how many of these different things are you looking at when you're examining scenes?
It's a very important and profound problem when it comes to multimodality, where you are not only looking at visuals, you have to correlate with what someone is speaking, for example. In Jurassic Park, there is a scene where it was explained how the park was being made because an insect got sort of sucked in sapling and etc. And then they could extract out the DNA, etc. So the main information there was in the audio stream, plus the visuals connected to the sapling, etc. So this is what we call as multimodality. The principle remains the same. It has seen a lot of these multimodal context previously. So it has seen people showing a visual and explaining these things so that when a new scene comes in, it's able to activate similar patterns. In some cases, we run maybe not multiple models, one model to capture the visual part, one model to capture the audio part, and then combine all the modalities together. If we can describe it textually, then we can model it.
Okay.
But there are also things which is beyond textual representation, things regarding aesthetics, for example, like some is a long shot, some is a wide shot. There are a lot of these filmmaking techniques that we are able to capture. Similarly for auditory things, some of the music is in a certain genre. So for example, something is very dramatic or something is quite soothing. So we are able to go and parse that kind of information also out. And one of the paradigms, especially in the last 4 to 5 years of machine learning research, is that people don't hand specify when something happens, do this. Rather, it tries to infer these patterns internally using a lot of data. And when a new stream of data comes in, a new video, for example, comes in, it's able to apply these patterns it has learned in the network into these novel use cases.
This process Appu's describing, where you have a model that's been trained on a bunch of data to recognize certain patterns, and then you use that model to identify those same patterns in new data, is called inference. Of course, I'm making this sound a lot easier than it actually is. Who you really want to hear from is Hicham Badri. He's the person responsible for helping Dropbox do inference as quickly and efficiently as possible.
I'm Hicham Badri. I'm a machine learning engineer at Dropbox. My work has always been focused on inference and making models run faster and cheaper. So before Dropbox, this was in 2017, so this was like super early stage. And we were trying to run computer vision models on the phone, for example.
Okay.
Without any internet connection, without anything. Because it was very expensive to run these models. We were exploring this direction of running models on phones. We saw that it took off like very well. So we started the company Mobius Labs to focus more on running models cheaper. And we did a transition from running models on the phone to running models for enterprise in their own servers. So my work was also basically trying to squeeze performance in that setup because obviously our previous clients didn't want to spend too much money on compute. So that worked very well. And last year we got acquired by Dropbox. And I'm basically continuing that work now more at Dropbox. But obviously a different type of work, but it's very related to what I was doing before. And it's also technically a very difficult thing to do. Like you want to squeeze as much performance as possible, which is pretty much the blocker right now for all the big labs like OpenAI, Anthropic, Google. All of them, they have exactly the same problem that I'm working on, which is how to unlock this intelligence, but don't break the bank, basically. Like, can you run this very expensive model on a very cheap GPU? It's a challenge, which is very interesting for me as well.
Why is search and content understanding so much more difficult with things like video and audio and images compared to text? Like, why is it so hard to make that content searchable?
Yes, I mean, simple answer is basically it's too much data to to process. For example, like if you take text, it's pretty simple, right? So the text becomes a set of what we call tokens, and then the model is going to process the tokens. If it's an image, it also gets converted into this kind of tokens. But the problem is it's too much tokens usually. Now you go from image to video. So a video is basically a bunch of images.
Right.
So for every image, you will have a set of tokens. But at the same time, you also have the audio, which is also requiring its own tokens. And the problem is like, there's a lot of things you can do like in a video. It's not just about understanding what is inside every frame, but it's also, for example, understanding how the visual information connects to the audio. Let's say it's someone in the kitchen, for example, they are talking, you can see them, and then they just disappear, but you still hear the audio of them talking. So if you connect the audio with the video, you will still understand it. It's the same person that is talking, for example, right?
Yeah.
But like if you just look at the video frames, you would not see the person. So it really depends on how far you want to go down the rabbit hole. And the further you go down, you might need actually different models.
Can you tell me more about how many different models we're talking about here? Like in Dropbox's context, for example, how many different models are we using to try and understand some of those complex relationships you're talking about?
So there will be pretty much like 3 models. So there will be like a model to understand the audio, just to transcribe the audio, having access to that information. And then you would have another model which would understand the image information. And then you would have a text model that will basically try to make sense of the summaries of each video segment.
Mm-hmm.
But I would say there's a 4th model which also understands the boundaries of the videos. So if there's a shot, it is to understand, okay, this is a scene. The scene has ended here. Now this is another scene. The approach we are following right now, which is like the easier way of doing this, is separating modalities. It just scales much better. And it's easier to serve and for inference cost, because you're basically decoupling things. It's not the best way to do it, but it's a valid way to do it at scale, because when you're separating these components, you can also iterate very quickly. You can, let's say, change, like there's a new model, let's say, understands images much better. You can just change that part. There's a new transcription model, which works very good, works with more languages. We can just swap that. And then we don't have to deal with all the headache of changing everything. So the current approach we are following is very good in terms of scaling and iterating, but it's not the best way to have like full understanding, because right now, for example, we see models that they are called omni-models, which is you have one single model that does everything, actually. It understands everything. So these omni-models, they are really, really interesting, because they can, like you can pretty much ask them anything, and you can give them like the audio and the images, and they will make sense of everything. But the problem is that they are very, very, very expensive to run. You cannot really scale it at the scale of like what we do at Dropbox. It's a lot of data. So you cannot like every time like run it through this huge model. So the direction is basically this way, is understanding everything, but also being able to generate it. There are already some models that do this. It's just that they are either not very good at something very specific, like say for audio, they would not be supporting many languages, for example, or they will have like mixed performance. They will not have the best performance for text, for example. If you're going to use a model like that, you want it to perform very well on all modalities. But yeah, as I said, this is the direction. It's like you would have like one big model that does everything.
I'm wondering if you can tell me a little bit about how you are able to do this work so quickly when it comes to search and understanding. Like, how is it that someone can ask a question and you can find the answer within an hours-long video in seconds.
So there's a lot of work on caching, and basically the work that you don't have to do on the spot, you do it beforehand, basically. So you upload the video, it's going to be pre-processed. That's the most expensive part. So this is where a bunch of models are running and trying to make sense of the data, etc. Then they are going to put the gist of it, let's say.
Mm-hmm. And they're doing that in advance. They're assuming some assumptions about what it is that people might want to know about that video or that piece of content.
Yeah, it's going to be analyzed and it's going to be, let's say, summarized. Then, because that part is going to take a lot of work. So this is going to be done. It's going to read the audio, understand the transcript, look at the video, understand all these segments and what is going on in the video. Then it's going to make a kind of summary of this. So when you go and there you search, it's not going and analyzing the whole video. It's basically just trying to search through this gist or summary. Let's say a question like, is there a dog in this video, for example? The model will basically, if you're chatting with it, it will basically connect that query to what it finds the video, and it will take that text and try to search through this summary to find the right segment, if that's possible or not. Mm-hmm. If there's actually a dog, it will say, for example, oh, in this video, I see a dog around this timestamp, like it's a golden retriever, blah, 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 blah.
I guess that's one of the advantages of being able to go and also look at external information, as being able to then actually identify what kind of dog it is. Like if you need to search the web for, different types of dog breeds or something.
Right now the models are really, really good at detecting and recognizing dogs, actually.
Okay. So we don't even need to do that.
Yeah, I think they are even better than humans at doing this. So basically 2 steps. The first step is this pre-processing, where we basically cache and make this kind of summary of the video, where we know temporarily what's going on. Once the video processed, someone comes, asks a question, we map the question to that summary with a model. It's got the embedding a model, and that's how basically the search happens.
Why do you want to make those models run faster? What's the benefit for the person on the other end of a Dropbox product when these models can process things faster and more efficiently?
Oh, yeah. It depends on the compute that you have access to. When we're talking about Dropbox, it's a lot of data. And if someone uploads a file or an audio file, for example, and they need to wait 2 days just to see the transcript, this is not a good product, obviously. Right? They want to upload, let's say, an audio file or video. They want to have access to the transcript within 1 or 2 seconds. But at the same time, what's going on is that the servers are actually processing a lot of files at the same time, right? So it's not there's one user and stop everything, let me just process for this user. It's a lot of users, they want the same experience. So this is where it's very important. It's first of all, without running things faster and cheaper, we would not even be able to offer the product. It's just not possible. And secondly, if we are able to offer it, is it a good experience for the user? So that's 2 things, actually 3 things. So the first thing is when they upload the file, how much time it takes to make that file searchable and accessible. But there's also the search part, where when you search, you want to get the answer very quickly. And the third thing is other scenarios where it's also very important to have access to fast inference. Let's say you're using some chat service, Dash, for example, or when you're chatting, right, you want to get the answer as fast as possible too. And that requires a lot of compute. And at the same time, as I said, there are a lot of people that also want to get the answer very fast. So it's a lot of compute that is needed to make everyone happy. And that's the challenge, basically.
What is it that you and your team are doing to actually make those models run faster and run more efficiently and do what you want them to do?
I mean, one solution is just throw money at it and just buy a bunch of a bunch of servers that are very expensive. I mean, if you see how much the labs are spending in terms of compute, it's the biggest expense. At our scale, we need to be a little bit careful because we do need to process a lot of data, but also we cannot spend billions of dollars on compute. So we need to find other ways of doing this. So the first thing we start with is the model choice. Obviously, we don't want the 1 trillion parameter model that requires a lot of compute because it's just too expensive to run, right?
Mm-hmm.
And also we don't need that much of a model because we could get basically the same performance with a smaller model. We will also see what kind of compute we have and go from there. So, okay, let's say, we have this type of GPUs. This is the biggest model we can run on these GPUs is this size. Let's find the best model of this size for our use case. Then we will run some benchmarks and say, okay, this is good. We will do this for a bunch of other models. We always keep an eye on the open source releases. So whenever there's a new model, we always go there and try to play with it and test it, because the trend that we see right now is that the smaller models are really catching up and they're becoming really, really good. For the same size, let's say a mid-size model, let's say 8-9 billion parameters this year is much, much, much better than what we had just 1 year ago. We have these separate modalities, right? And we try to find the best model for each modality and keep an eye on open source releases whenever there's a new model. So that's one part. It's the choice of the model. Make sure that the choice of the model is compatible with the amount of compute we have. Then the other thing is, okay, well, now we have this model. How can we run it very fast? So this is the part where we will look into different things. So we will look into quantization. And quantization is basically you take this model, which is a little bit big, and you make it kind of smaller and faster. That part is very hot topic. Everyone is using some kind of quantization. So once the model is quantized, we also need to know how to run this quantized model fast. So this is the part where we will need to look into what is called GPU kernels. And these kernels are very important because if you quantize this model and you don't have the right GPU kernels, they are not going to run fast at all. So there's the model size, choosing the right model size based on the compute we have. Then there's all the work on making the model actually run faster. So there's the quantization work, there's the kernel choice. So it's not just the model running, but everything around the model. So that's an exciting part for me.
A lot of the work that you did at Mobius Labs was open source, and that's still the case at Dropbox. Why is open source important to you?
I think open source is the best way to learn. I don't think I would have learned the things that I have learned without open source, because you share it and people use it. And also it's the best way to discover bugs and discover what things work, discover what people are looking for. If it's popular and people are using it, it's going to get better because people are going to raise issues. They are going to tell you what works, what doesn't. It makes your software better because people will test it and some experts will collaborate with you, which is great because if you're just doing that within the same company, everything is closed. You would never have the opportunity to talk to people from OpenAI, from NVIDIA.
Sure.
They are really experts and they will say, okay, what you're doing here, you could do it maybe better this way, etc. And you will never be able to figure that out alone because maybe they will think about something that you have never thought about before. So that's why for me, it's very, very important.
Hicham, thank you so much for joining us. This was really nice.
Of course, it was a pleasure talking to you.
Before we wrap things up, there's something Appu said at the beginning of our conversation that I want to revisit. Earlier on, you said that part of the reason why you got into this line of work in the first place is you wanted to take your love of films and cinema and combine it with sort of the world of computer science. And I wonder whether you feel like you have achieved that.
So it's an interesting question in the sense that if this end state was presented to me, like if you go back 10 years back and said, this is what we have achieved, I would have been super happy, essentially.
Mm-hmm.
But right now, what we built 6 months before is getting deprecated within 6 months because the community is moving very fast.
Mm-hmm.
So right now, I'm much more excited because we feel the scope has actually increased much more drastically. And again, we still don't have the data of Star Trek, so there is still big things to build, essentially. So.
Of course, Dropbox can neither confirm nor deny any current or future plans to develop a data-inspired Android. But in the meantime,
Dropbox has always been trusted with our customers' most important content. AI makes that responsibility even more important now because it changes how quickly people can find, synthesize, and act on that information.
how do you keep your content safe and secure in this new world of AI tools? That's on our next episode of Working Smarter. We'll see you then. Working Smarter is brought to you by Dropbox. Find, organize, and share your work all in one place with context-aware AI from Dropbox. You can listen to more episodes of Working Smarter on Apple Podcasts, Spotify, YouTube, or wherever you get your podcasts. And you can also find more interviews like this one on our website, workingsmarter.ai. Working Smarter would not be possible without the talented team at Cosmic Standard, producer Ben Montoya, sound engineer Asia Simpson, technical director Jacob Winnick, and executive producer Eliza Smith. Special thanks to our illustrator, Fanny Lohr, and to Megan Ellingboe for marketing support. Our theme song was composed by Doug Stewart, and I'm your host, Matthew Braga. Thanks for listening.